Hello and welcome to today's lesson, section 4.3. We're going to solve homogeneous linear equations with constant coefficients. Now, consider the first order homogeneous linear differential equation with constant coefficients. So a y prime plus b y equals 0. If we are given a first order, homogeneous linear differential equation, and we see that if A and B are both going to be constant coefficients, then more than likely what happen is that you're going to have some y that when you take the derivative of y, it's just going to be y times a constant itself, so k. So y prime is equal to k times itself. Now, if you can think of, okay, what are some functions when I take the derivative, it's, a constant times itself. Well, then that's when you get the exponential. So again, over here is kind of that example where we have y prime e to the ky, where k is just going to be that constant. It's going to be the original y. And so if we make y equal to e to the kt, then when we take the derivative of e to the kt, we're going to get k e to the kt, which is really just y prime is equal to k y, because y is e to the kt. All right. So now we know what our first integral has to look like. Through inspection, we know that it's going to be, e to the kt. Now we've got to find, okay, well, what is that k? What is that constant of the function? So what we're going to do is we're going to take our solution, all right, which we say y is equal to e to the kt, y prime is k e to the kt, and we're going to substitute that in for y prime and y. And that's how we get k e to the kt times a and b times e to the kt. Now, let's go ahead and solve this. So, one thing we do know is that because they both have e to the kt, we can pull out an e to the kt. So, I have e to the kt times ak plus b. Now, we know that e to the kt is never going to equal 0. Because it's never going to equal 0, we can set ak plus b equal to 0. Setting ak plus b equal to 0, what we're going to do is we're going to go ahead and substitute that in, and we're going to say ak plus b equals 0, solve for k, and k is equal to negative b over a. And so now we've solved and we found our solution. So since it's a first order, there's only one solution. Y is equal to c sub 1 e to the kt, where k is negative b over a. And again, always multiply by that c sub 1 constant. Alright, now let's see if this works. So we want to solve 3y prime plus 2y equals 0. Again, we're going to say y is equal to e to the kt, y prime is equal to k e to the kt. We're going to plug those into our differential equation. So y prime, 3y prime plus 2y is equal to 0. We can pull out an e to the kt. We're left with 3k plus 2. We're going to set that equal to 0 and solve. When we set that equal to solve, we know that k is equal to negative 2/3. And so therefore, our solution is y is equal to c sub 1, some constant, times e to the negative 2/3 t. And again, you can check that by just plugging that in and seeing if it holds true. Alright, let's go ahead now and look at the auxiliary equation. So consider we now have a second order differential equation. I represent it here by 1, where a, b, and c are constants. We try to find a solution of the form y equals e to the mx. Again, it is going to be a solution of y equals e to the mx because a, b, and c are constants. If they're not constants, then we can't really use this. Alright, so if y is equal to e to the mx, then I know that y prime is just going to be me to the mx, and y double prime is going to be m squared e to the mx. Substitute that in. We're given this equation, we can pull out the e to the mx, and then times a m squared plus 2m plus c equals 0. Now what we're going to do is we're going to set that equal to 0, and we're going to be able to solve for m. So when we pull out the exponential, and we're left with am squared plus bm plus c equals 0, that's called the auxiliary equation, or the differential equation. So we're going to have three cases when we solve for m. The first time is, when we have this, auxiliary equation, which is going to be a quadratic equation, and we find solutions, m1 and m2 are going to be different. So our two solutions for that, auxiliary equation, they're two different numbers, all right? If there are two different solutions, then our y sub 1 is just going to be c sub 1 e to the m sub 1 of x, and then y sub 2 is going to be c sub 2 times e to the m sub 2 x. So, again, something that's very easy. Once we factor and we find m, we can go ahead and plug that into our, our formula. We can go ahead and plug that into our y. Make sure that we multiply that c sub 1 and we found the solution. Now, what if we have repeated real roots? If we have repeated real roots where m sub 1 and m sub 2 are going to be the same, so when we solve for m in our auxiliary equation, we have the same value, well, we can find the first one pretty easy. It's going to hold true. It's going to be y sub 1 is equal to c sub 1 times e to the m sub 1 of x, m sub 1 times x. Now, we can't just say y sub 2 is also the same thing, because then we don't have a new solution. It's just, the same solution repeated. So we know that there are going to be two different solutions. So to find the second one, what we're going to do is we're going to go back to reduction of order, where we can say, well, we already have one solution to the differential equation. Let's find the second by taking the second solution, dividing it by the first, and we know that that's going to equal some function, back to yesterday's notes. All right, now, when we do the reduction of order formula, we're going to know that y sub 2 is equal to m times m sub 1 of x, so that's like the y1, times the integral. Now, what we said here was, when you do it, you're going to get, for your value where you take the integral, your p value, it's going to be negative b over a. Kind of what we got at the very top. We're going to make that 2m sub 1. So when we make that 2m sub 1, what we're going to be able to do is when we take the integral of that, it's going to be 2m sub 1 of x. So that when we have the integral, it's going to be the numerator and denominator are the same. That cancels out to be 1. So we have the integral of just dx. So if we have e to the m sub 1 of x times the integral of dx, that's just going to be x times e to the m sub 1 of x. And that's going to be our general solution. So this is our second solution. All right, x e to the m sub 1 of x. So that m sub 1 stays the same. We now just have an x. And the general solution is going to be y equals c sub 1 e to the m sub 1 of x plus c sub 2 x m sub 1 of x. Now, say it was a triple repeated root. Our next solution, if it's a triple repeated root, it's just going to be plus c sub 2 x squared e to the m sub 1 of x. If we added another solution of another repeated root, it's going to be c sub 2 times x cubed e to the m sub 1 of x. So I just wanted to throw that in there so that you know what happens if there's a triple repeat. All right, and that's going to be it for this one. I'm going to talk about the conjugate complex